All right, I was trying to come up with some good YouTube videos with, professional voice actors and good animations, and none of them quite fit. So I'm going to try to look through the notes a little bit here and see what we've got and kind of explain what we're up against here. All right, what we're looking at is calorimetry. This is how we know what we know. You guys did this in biology, where you were burning things and you measured the temperature change of the surroundings, the water, whatever was in there, and that told you how much heat was released. So all of those values on that Appendix C we've been using come from this kind of experiment. So our first term with calorimeter, this is basically a device in which a temperature change of a substance of known specific heat is measured. Kind of like with titration, we're comparing unknown to known. So the substance that it refers to 99% of the time is water because it's cheap, it's easy to work with, and it is very well understood. So by looking at how the temperature of the water changes, we can see how much heat was released or absorbed by the reaction. If the water temperature goes up so many degrees, based on how much is there, that corresponds with a certain number of joules of energy. If it goes down, that corresponds to a certain number of joules of energy. Exothermic, endothermic. Now, I throw this one in here just kind of as a thought. Bomb calorimeter. The difference between a regular calorimeter and a bomb calorimeter is that the regular calorimeter is open. If you're going to do something that's going to generate a gas, you're probably going to need a regular calorimeter. A bomb calorimeter is where the container with the reaction is completely submerged in the water. And the reason I mention this is because this is ideal. Because this way, any energy coming out of the reaction is going into the water. And this kind of gives us a closed system, so we're not losing anything. Now, all calorimeters work pretty much the same way. They have pretty much the same parts. The calorimeter itself is just the container. It has a thermometer, something to measure the temperature, beginning temperature, ending temperature. It's full of some substance, usually water, occasionally ice water, occasionally some kind of oil, but yeah, usually water. And then we have the reaction vessel. If it's a bomb calorimeter like this one, okay. If it's an open calorimeter, that would look more like a test tube down in there. And then the reaction itself. Now, with that, we're looking at the calculations. And I'm not going to dive too deep into these today. I'm going to go over the basic ideas. I'm going to give you some problems to work on that was in the message I sent out. And what it all comes down to is this, and to the point where I recommend just write this down at the top. I know how most people feel about extra steps, but this is the concept. Heat lost equals heat gained. Now you can divide this up a couple of ways. We have heat lost by the reaction, and we're talking in terms of an exothermic reaction. And rather than rewrite this whole thing, if it's an endothermic reaction, just reverse everything. It becomes heat gained by the reaction and heat lost by the calorimeter in the water. Now, looking at that, the reaction releases heat. Ideally, in a perfect world, it would all go into the water. And in a good calorimeter, the vast majority of it goes into the water. But we also have some that doesn't. Now we say heat gained by the calorimeter. We often refer to this as the calorimeter constant, but that includes the surroundings. That's the calorimeter, that's the thermometer, that's the air, that's the table, that's you, that's your third cousin William in Ohio. It's anything but the water. We lump it all together. Now, the thing with a calorimeter constant, and we'll do a little bit of this in the lab, is that it's predictable. We can sort of zero in a calorimeter. If we know how much heat escapes, we can figure that into our calculations, and that will be consistent for that device. Now, our equation is this. Our heat, Q, equals the specific heat times the mass times the temperature change. Doesn't matter what the starting temperature is, what the ending temperature is, it only matters how much does the temperature change. Now, we've seen this in regular chem. You guys have worked with this equation. We're not really going to do anything with phase changes here. That's a whole other thing, and it's interesting, it's useful, but it's not useful enough to be worth the time. Now, the specific heat is specific to a certain material. There are two terms you're going to hear bounced around in your book. One is heat capacity, and heat capacity is a collective term. Like we say, the heat capacity of the calorimeter all together as a unit. Or we can even say the heat capacity of the water. Specific heat capacity is talking about the material, and it is per gram. So a heat capacity would be joules per degree Celsius. For this object, this calorimeter, this amount of water, it takes this many joules per each degree Celsius. With specific heat, we can have different amounts of the material. It's a little more flexible. So here, the specific heat times the mass times the temperature change, and that'll give you the joules of energy. Now, specific heat is an interesting, term, not really term, but property of a material where they vary wildly. And some materials, if I put the same amount of energy into 10 grams of iron and 10 grams of copper, the temperature of the copper will go up more. Now, water has a particularly high specific heat, as anyone who's ever gone camping around a lake knows. It takes 4.184 joules of energy to raise 1 gram of water 1 degree Celsius, which means at 10 o'clock in the morning, the lake is still freezing cold because it has to absorb a huge amount of energy to raise the temperature. If I took pretty much almost any other material and set it out there, absorbing that same amount of energy would heat up much faster. It also means that at 10 o'clock at night, the water of the lake is still warm because it has to lose a huge amount of energy for the temperature to go down. And this is why when you talk about the Caribbean Sea, that's what fuels our hurricanes, is the water temperature. And it's difficult to explain to people why the weathermen are getting all, bent around the axle about, 2 degrees. It's like, oh no, the water temperature went up 2 degrees, big deal. Well, you take 2 degrees times a billion tons of water, what we have there is a truly phenomenal amount of energy. One of Donald Trump's many interesting ideas, as you know, love him or hate him, he got up in front of a microphone and spoke whatever was on his mind. One of his ideas was dropping nuclear weapons into hurricanes to disrupt them. Frankly, I think he had watched the first Sharknado. But the problem with that, well, first, it'd be an epic environmental disaster. Secondly, the energy released from the nuclear bomb, not even close. So when we're talking about a slight temperature shift in water, we're talking about a significant amount of energy. And that's something we'll look at a little bit more on Monday. So looking at this, and we're going to, like I said, go for kind of a simple one here. How much heat is necessary to raise the temperature 40 grams of water 18 degrees Celsius? So I want you to pause me right now, figure this out, come back. Hey, welcome back. All right, so we have our equation. Specific heat of water, 4.184 joules per gram degree Celsius. We have 40 grams of water, 18 degrees Celsius. So that means it's going to take 3,000 joules or 3 kilojoules. When we're dealing with any significant amount of energy, we very quickly find ourselves working in kilojoules. You know, joules, even when you're talking about thousands of joules, is not a large amount of energy. Okay, so that is that. Go through, work through the problems I gave you out of the book. You can skim over section 5.5, to get some perspective, ideas on those. One of those problems is a red problem, so I would do that one first. That's why I listed it on the list first. Check your answer, make sure you're on track, and then do the other ones. All right, have a good day. Bye-bye.